In this lecture, we'll talk about composite functions. So let's start with the definition. Given two functions, f and g, the composite function, denoted by f circle g, read f composed with g, is defined as follows. F circle g of x is equal to f of g of x. So you take the function that's on the right-hand side of the circle and plug it into this function that's on the left-hand side. The domain of f circle g, or f composed with g, is the set of all numbers x in the domain of g, such that g of x is in the domain of f. So, if we think about this graphically, we start with a set of numbers that's the domain of the function g, and x is inside that domain. Then the function g will map that x into the range of g, represented by the blue circle on the right, and that range of g intersects with the domain of the function f, and g of x needs to be in both the range of g and the domain of f in order to go into the function f. So g of x goes into f, and then that gives us the composition f of g of x. Here's another way to think of it. So we have a value x that we're going to input into the function g. So x goes into g, and that gives us the result, g of x, which is going to go into the function f, and that results in the composition f of g of x. So let's look at a couple of examples. First, consider the example where f of x is equal to 3x plus 2, and g of x is equal to 2x squared minus 1. First, we want to find f composed with g of 4. So, in order to find f composed with g of 4, we'll take g of 4 and plug that into f. So to find g of 4, we plug 4 in for x in the function g. So this is going to give us f of 2 times 4 squared minus 1. If we simplify that, we get 2 times 16 minus 1. And we simplify it further, that gives us f of 31. So we'll plug 31 into x for the function f, which will give us 3 times 31 plus 2, which if we simplify will be 93 plus 2, which is 95. So f composed with g of 4 will be 95. Now let's look at f composed with f of 1. So to evaluate f composed with f of 1, we'll take f of 1 and plug that into f. So first we evaluate f of 1 by plugging 1 into f. So this is going to give us f of 3 times 1 plus 2, which if we simplify will give us f of 3 plus 2, which is f of 5. So we plug 5 into the function f, which will give us 3 times 5 plus 2. If we simplify the multiplication, that'll give us 15 plus 2. And so we'll have f composed with f of 1 is equal to 17. So let's look at another example. This time we have f of x equals 2x squared, and g of x equals 1 minus 3x squared. And we want to find g composed with f of 2 and g composed with g of 0. Take a few minutes and see if you can figure these out yourself. So take a few minutes, try to answer these two questions. When you feel like you have an answer, continue the lecture and work along with me to see if you got it right. So we'll start with g composed of f of 2, which means we'll take f of 2 and plug that into g. So to evaluate f of 2, we'll plug 2 in for x in the function f. That'll give us 2 times 2 squared. If we simplify it, that'll give us 2 times 4, which is 8. So we're looking at g of 8, which means we plug 8 in for x in the function g. That'll give us 1 minus 3 times 8 squared. 8 squared is 64, so we have 1 minus 3 times 64. Gives us 1 minus 192, which simplifies to a negative 191. So, g composed with f of 2 is negative 191. Now let's look at g composed with g of 0. So to evaluate this, we'll take g of 0 and plug that into g. So first we evaluate g of 0 by plugging 0 in for x in the function g. So that'll give us g of 1 minus 3 times 0 squared. And 1 minus 3 times 0 squared is just 1, so this gives us g of 1, which we can evaluate by plugging 1 in for x in the function g, which will give us 1 minus 3, and that simplifies to negative 2. So g composed with g of 0 is negative 2. Alright, next we want to determine how to find the domain of a composite function. So let's assume that we're working with the function f composed with g of x, where g of x is going to be plugged into f. To find the domain of this composite, we're going to take two steps. First, we find the domain of g of x, which is the inner function, and exclude any values that are not in the domain of g. Second, we'll find the domain of f of x, which is the outer function, and for any values that are excluded from f, we're going to find out what value of x such that g of x equals those values. So, for instance, if x could not be equal to 2 for f, we need to find out what makes g of x equal to 2. So we're going to look at a few examples where we find the domain. First, consider f of x equals negative x, and g of x equals 2x minus 4. Let's find the domain of f composed with g. So we start by considering the domain of g, which is our inner function, and the domain of 2x minus 4 is all real numbers, so there's nothing that we need to worry about excluding. Next, we look at the domain of f, which was our outer function, and the domain of negative x is also all real numbers, so we don't have to worry about excluding anything there. And so the domain of f composed with g will be all real numbers. So let's look at another example. This time we have f of x equals 1 over x plus 3, and g of x equals negative 2 over x. And we want to find the domain of f composed with g. So g is our inner function, f is our outer function. So we start by considering the domain of g, the inner function. Since g is negative 2 over x, we need to make sure that we don't have a 0 in the denominator, and so that means that x cannot equal 0. So x cannot equal 0 is the domain of g, so 0 will be excluded from the domain of our composition. Next, we look at the domain of f, which is the outer function. Since f is 1 over x plus 3, again we need to make sure that the denominator is not equal to 0, so that means x cannot equal negative 3. But we don't just exclude negative 3 in this case, we need to find out what value of x would make g of x equal to negative 3. So we need to make sure that g of x cannot equal negative 3, since g of x is what's being put into f. So negative 2 over x, which is g of x, cannot equal negative 3. If we multiply both sides by x, we get negative 2 cannot equal negative 3x. And then we divide both sides by negative 3, and we get x cannot equal 2/3. So 2/3 must be excluded from the domain of the composition. So the domain of f composed with g is going to be the set of x, such that x does not equal 0, and x does not equal 2/3. Let's look at one final example. This time we have f of x equals x minus 2, and g of x equals the square root of 1 minus x. And we want to find the domain of f composed with g. Take a few minutes and see if you can figure out this domain on your own. Again, once you finish, continue the lecture, and we'll go over it together. We start by finding the domain of g, which is the inner function. Since g is a square root in it, we need to make sure that whatever's under the square root sign is a positive number. So 1 minus x has to be greater than or equal to 0. So, if we solve that, 1 minus x is greater than or equal to 0, we wind up with x is less than or equal to 1. So this will be a restriction on the domain of the composition. Next, we look at the domain of f, which is our outer function, and since f is x minus 2, that's just a polynomial, the domain will be all real numbers. So we don't have to worry about this affecting the domain of our composition. So the domain of the composition, f composed with g, will be the set of x such that x is less than or equal to 1. So next we want to talk about finding a composite function. So if we have the function f composed with g of x, that means we plug the function g of x into f. So let's look at an example. Consider the functions f of x equals negative x and g of x equals 2x minus 4. We want to find f composed with g, g composed with f composed with f, and g composed with g. So let's start with f composed with g. This means we'll plug g of x into f. So plugging g of x into f gives us f of 2x minus 4, which will be negative 2x minus 4. If we plug 2x minus 4 in for x in f, and if we distribute our negative sign, that'll give us negative 2x plus 4. Next, let's look at g composed with f. So this time we'll plug f of x into g. So to plug f of x into g, that means we'll plug negative x into g, which will give us 2 times negative x minus 4, which simplifies to negative 2x minus 4. Next, we'll consider f composed with f of x. So this time we'll plug f of x into f of x. So to plug f of x into f, we'll evaluate negative x in f. So that will give us negative x, which simplifies to be positive x. And finally, if we consider g composed with g, that means we'll plug g of x into g of x, which means we plug 2x minus 4 into g of x, which gives us 2 times 2x minus 4 minus 4. If we distribute the 2 through the parentheses, we get 4x minus 8 minus 4, and this simplifies to 4x minus 12. Let's look at one last example of creating composite functions. Let's consider f of x equals 1 over x plus 3, and g of x equals negative 2 over x. Again, we want to find f composed with g, g composed with f composed with f, and g composed with g. So we'll start with f composed with g. This means we plug g of x into f. So we plug negative 2 over x into f. That gives us 1 divided by negative 2 over x plus 3. If we want to simplify this, we need to get a common denominator in the denominator of our fraction. So we'll rewrite 3 as 3x over x. So now we can combine the denominator. This gives us 1 over negative 2 plus 3x over x. And to simplify that, we just take the reciprocal. So f composed with g will be x over negative 2 plus 3x. Next, let's look at g composed with f. So this time, we'll plug f of x into g. So that means we plug 1 over x plus 3 into g. So that'll give us negative 2 divided by 1 over x plus 3. Remember, to divide fractions, you multiply by the reciprocal of the denominator. So this is negative 2 times x plus 3 over 1. And so if we simplify that, that gives us negative 2x minus 6. Alright, so continuing our example, we're going to consider f composed with f of x. So that means we plug f of x into f. So that means we'll plug 1 over x plus 3 into f, giving us 1 over x plus 3 plus 3. Again, to combine the denominator of this fraction, we need to have common denominators there. So we're going to rewrite 3 as 3 times x plus 3 over x plus 3. And so that'll give us 1 over x plus 3 plus 3x plus 9 over x plus 3. We can combine the fractions to give us 1 over 3x plus 10 over x plus 3. And finally, we evaluate that by taking the reciprocal. So f composed with f is going to be x plus 3 over 3x plus 10. And finally, we look at g composed with g. So we'll plug g of x into g, which means we'll look at g of negative 2 over x, which is negative 2 divided by negative 2 over x. And again, in order to divide fractions, we multiply by the reciprocal. So this is negative 2 times x over negative 2, which simplifies to give us x. So g composed with g just gives us x. And the last thing we want to talk about in this section is finding the components of a composite function. So if you're given an overall function, you could write it as a composite function by looking for a function within a function. Now let's do an example or two to see if this makes sense. So for example, we're given capital H of x equals 1 plus x squared quantity cubed. we want to find functions f and g such that f composed with g would equal h. So g is our inner function and f is our outer function. We want to look at this and see if we can determine two functions that can be written so that h is written as a composition. So if you look at h, do you see a function within a function? So when I look at h, I see 1 plus x squared inside the cube function. So we can break it up into those two functions. F of x would equal x cubed, that's our outer function, and g of x would equal 1 plus x squared, that's the inner function. Of course, when you're writing the components of a composite function, there's often multiple answers that could be true. So another way we could look at this is our outer function is the function 1 plus x quantity cubed, and our inner function, g, is x squared. So notice if you plug x squared into 1 plus x quantity cubed, that will also give you the h that we started with. Here's one last example. Given the function capital H of x equals the square root of 1 minus x squared, find functions f and g such that f composed with g will equal h. So take a couple minutes and see if you can find an inner function and an outer function so that when you put them together, they give you the function we started with. Remember, there can be multiple answers to these types of problems. So see if you can figure one out and then continue the lecture to see what I've done. So again, when I look at this, I see an outer function of the square root function. So f of x will equal square root. And what's under the square root is 1 minus x squared, so our inner function would be g of x equals 1 minus x squared. And of course, an alternative, we could do like we did with the previous example. Let's do f of x equals the square root of 1 minus x. And then in this case, g of x will equal x squared.